Hi guys, I thought I'd make another video to show you, to give you some additional information about the way in which plane waves are incident on media from an oblique angle. Okay, so the problem that I have, or the case that I would like to look at, is this case over here, where I have a normal electric field. This is my EI, right? So over here, and it's coming out of the page. So it's, if I consider this axis where X is on top and Z is at the bottom, then Y is pointing out. Okay, so in this case, my plane of incidence, let's write it, plane of incidence would be the XZ plane. Okay, so normal to the plane of incidence would be any vector in the Y direction, like for example EI over here. Okay, so EI is incident on this interface between region 1 and region 2. So let's highlight that. I have region 1 over here and I have region 2 over here, and this part has its own characteristics, maybe epsilon R2, and this one is epsilon R1, and we are considering in general non-magnetic material over here, so I'm working with the case where mu is just equal to mu0 in both. Alright, so from these two parameters I then also have obviously intrinsic impedance for this part, that's eta 1 on this side, and I have eta 2 on this side over here. Okay, so the goal of this part of the work, which is essentially covered in from about lecture 14 or section 8.10 8-10.2 in the textbook, is how, if we know this, right, so we know the incident electric field, we know its direction, and obviously from these two we can calculate the magnetic field. If we know this, how can we find that which is the transmitted field, right? So the field that will transmit at some angle theta r. We want to know this angle as well, and then we want to know what is the reflected field. So ER is over here. Let's just say it comes out of the board, and then the direction of propagation of this reflected field is in this way. Then HR has to be in that direction over there. Okay, so something that I've covered in class, and that it's also in the tutorial test, is if you know what the propagation directions are here, and you know what the electric field is because you assume normal incidence, right? Then can you write down the magnetic field directions? And all you essentially do is you use the fact that power will propagate in the direction of, so let's just say A and I will propagate in the direction of E cross H. Okay, so if you follow the convention that E cross H should point in the direction of this vector over here, and the same for the transmitted and reflected fields, then you will always have the little package in the correct convention where E cross H gives you A and I. Same with the other vectors over here. E transmitted cross H transmitted should give you the propagation direction of the transmitted field, and here, because the reflected field is pointing backwards, E cross H goes in that direction over here, and H is pointing up like that. You'll note that EI and ER is in the same direction, and here it's all pointing in the same direction. That's okay, right? So you could have also selected ER to go into the board, but then your direction for H would have changed. So, but we keep them all the same, just for simplicity. And what is important is the way in which E and R is defined relative to each other, because I know this vector has to point in that direction of the reflected field. Okay, so our goal now is to find this transmitted field and this angle, and this transmitted field and this angle, this theta r. Let's just write it a bit clearer, that theta r, and this is theta t. sorry, over here, there's theta t, theta r. In terms of theta I, and also there's unknown coefficients associated, obviously, with this this transmitted and reflected field. Okay, so cool, let's do that. How are we going to do that? So I'm going to move up my system over here a bit. It's a makeshift system at home, so I apologize if it's a bit blurry, but I think it should be okay. All right. Okay, how are we going to start? Well, obviously, the first most important thing is make sure your sketch is correct. Make sure your direction of H is correct, given the direction of of E and A and I, and same with all the other components. All right. So draw the sketch, make sure it's 100%, and then you tackle the problem. Okay. So it's right here. Step one is we would like to find a NI, ANR, the propagation direction of the incident, reflected, and the transmitted fields. Né? That's the first thing that I've got to figure out how to do. And I'll show you now why we need to figure that out. But we want to describe this vector in terms of these angles. That's pretty straightforward. So let's look at this one over here, ANI. I'm going to look at the little axis over there. Let's draw it out. It's pretty simple, right? So I can do it a bit more clear. I have my X vector on the top, and I have my Z, and this just follows from my definition of the problem, right? So I have that, and then I have ANI over here, and this angle, if you follow just trigonometry, this angle over here, if I have a little local axis, should also be equal to that angle. So this is theta I. Okay. So what happens then is A and I can be expressed as, in the x direction, I have sine theta I. In the x direction, plus cos theta I, this component over here, in the z direction. Okay. Then I can do the same now for that vector over here. Let's look at it. And obviously in the tests and exams you'll go a little bit, you'll speed things up a bit. Eh? You don't have to, you can also just draw your little local coordinate axis over here and here, and just do this very quickly. I'm just now elaborating on this point so that it's nice and clear. Okay, so I have A and T over here, and I have theta T, and this is just, this angle is the same as this angle over here. All right, so A and T is equal to, it'll be sine theta in the AX plus cos theta T in the AZ. Okay, now looks the same, which makes sense because they are essentially orientated in a very similar fashion. And what about my reflected propagation vector over here? Okay, now this one goes backwards. Let's see where I can, that's Z, this is Z. Let's see where this vector points over here. Okay, well, this is not T, this is R. Okay, sorry. If I look at my picture, well, same thing. That angle is the same as this angle, which is theta R. Okay, so ANR is equal to sine theta R in the in the x direction, minus, because it's pointing in the negative z, sorry, plus z, it points in that direction. This is negative z, so it's minus cos theta r. This component over here, that vector cos will give you that in dAz. Okay, so now I have my propagation directions expressed in terms of this angle, and this angle. Cool. Next up, so now that I have these, what can I do? Well, the second step is I can now find mathematical expressions for EI, ER, and ET. And that's pretty simple because I know from the lectures that if I look at some point R equals to X, Y, and Z, then an electric field vector is expressed as can be expressed as some vector that looks like this: minus j beta a n dot r. Okay, where that component is the direction into which in which this field is propagating, and that's just some arbitrary position x, y, z, and that is a vector. But I know what those components are because I have to find my electric field perpendicular to my plane of incidence. Okay, so let's start expressing now my field vectors EI, ET, and ER in terms of this equation over here. Let's do that. So I have EI is equal to, I'm working in the y direction, EI is coming out of the board or out of the page over here. So it's I'm giving it a coefficient EI0 e to the minus j beta 1. This is important, this subscript 1. This 1 tells me that I'm working in region 1. If I'm going to use a 2, it's going to indicate that I work with the field, which is obviously just the transmitted field in region 2. Okay, so it's AY EI0 e to the minus j beta 1 ANI dot R. Okay, and this is equal to AY EI0 e to the minus j beta 1, because ANI expressed like this dot R, well, only the x and z components will remain because there is no y component. So it looks something like this: x sine theta I plus z cos theta I. This is all part of this exponential argument, right? Okay. So I have an expression for my incident electric field. What about my reflected field? ER is equal to, it's also in the y direction. There, look at this, it's coming out. We're looking here now, sorry. This one is coming out, so it's in the AY. And I'm giving it some coefficient ER0 that I want to determine later. Same thing, e to the minus j beta 1 ANR dot R. And this is AY ER0 e to the minus j beta 1 x sine theta r minus z cos theta r. Okay. And obviously the transmitted field works exactly the same. This one comes out of the board, AY, some unknown coefficient, ET0, e to the minus j. But now take care, beta 2, I'm giving it a subscript 2 because I'm working in region 2. E to the minus j beta 2, ANT, this vector over here, dot R is equal to AY ET0 e to the minus j beta to x sine theta t plus z cos theta t. Okay. Now I have my electric fields expressed, well, they are obviously functions of x and z, expressed in terms of my angles, theta I, theta t, and theta r. Okay. One part of the fight is over. Let's figure out now what is hi, hr, and ht. What are these? Remember your vector signs over here. What are these vectors? The magnetic field vectors. How can I also find them? And that's should be pretty simple. Okay guys, so now we're going to find the magnetic field vectors. We already have our electric field vector expressions. Let's find our magnetic fields. The first thing that so let's say this is now step 3. Find for me hi, hr, and ht. The incident, reflected, and transmitted magnetic fields. Given that I already have expressions now for the electric fields. So you need to recall a quick way in which to go from the electric field to the magnetic field is that I can use, I'm looking at some arbitrary position r. This is a very useful expression where if I work with, I know that my magnetic field is perpendicular to the electric field, and that's perpendicular to the direction of propagation given by this vector n. So I can use this expression to find my magnetic fields. This is also in the textbook. Okay. So let's go for it. Hi is equal to, remember I already have expressions for my electric fields. I'm just going to flash that page again so that you recall we were deriving it. So this is my electric field expressions. Look something like this. My reflected electric field and my transmitted electric field. These are the expressions that I have for them. They have a y component and some exponential that is a function of both x and z, and the angles theta I and theta I, theta r, and theta t for the reflected and transmitted fields respectively. So let's just look at this one. I have EI is equal to AY, some value over here. Okay, and the other thing that I know is I also know what this direction vector is. That I also calculated. So I'm going to slip over here. I calculated ANI as sine theta I AX plus cos theta I AZ. Okay, so I have both ANI and theta R. And then I can just use this expression to find my magnetic field from my electric field. So what I have is I have 1 over, let's write it out now. Obviously in the test you'll go a little bit faster. ANI, that's my direction of propagation of my fields here, cross my electric field, which is AY, EI0. I'll bring this back when we need it. Let's just make some space over here. So it's EI0, e to the minus j beta 1, x sine theta I plus z cos theta I. It looks like this. And this one I can also expand, and it will look like this. 1 over eta 1 sine theta I in the x direction plus cos theta I in the z direction cross AY EI0 e to the minus j beta 1 x sine theta I plus z cos theta I. Now, this is where your cross product should not let you should not disappoint you. Okay, so what I do to just easily do AX cross AY and AZ cross AY, because that's in effect what my yes, this is exactly, we need to do AX cross AY and AZ cross AY, is I draw a little axis over here in the sideline of my paper. So I have AZ, AX, and AY. This is a right-handed coordinate axis. So that if I follow my right hand, look at my fingers, AX cross AY, my fingers points from AX to AY, my thumb will point in the direction of AZ. So X cross Y will give you Z. So X cross Y will give you Z. Z cross Y, Z cross Y, if I follow my right hand rule, will point in the minus X direction. Okay, so this becomes EI0 over eta 1, just taking that term, bringing it in front, times minus cos theta I AX. This is now this cross this. I'm just writing my X in front. So cos theta I AZ cross AY, AZ cross AY gives you minus X, which I have over here, plus AX cross AY, so AX cross AY gives plus Z, and I have plus sine theta I in the AZ direction, e to the minus j beta 1 x sine theta I plus z cos theta I. Okay. Alright, so that's an expression for HI. Now, how can I check this? Make sure that it's correct. I can check this by looking over here, right? So, let's put it here. So H has some component in the negative x direction, some component in the negative x direction, and then some component in the plus z direction, some component in the plus z direction. Okay, so this is just a visual confirmation that my math is working out fine. Okay, now I can do the same for the transmitted magnetic field and the reflected magnetic field. So let's just quickly do this. So my transmitted magnetic field is, let's work with the reflected field first. So this one over here. So I'm expecting some positive x component and some positive z component. Let's see if this is what we're getting. So HR is equal to 1 over eta 1. Remember, I'm working in region 1, which is over here. So region 1 there. So that's why I have eta 1. That's the direction in which my field is propagating, ANR. There we go. So that's this part over there. Cross ER. And I already have an expression for this, right? So this just becomes, I'm going to substitute in the equation that we derived for this one. So it's 1 over eta 1. Let's do this. It's sine theta r in the x direction minus cos theta r in the z direction cross now my expression for ER, which is AY ER0 e to the minus j beta 1 x sine theta r minus z cos theta r. Okay. And if I just perform this, x cross y, which I already know now, x cross y gives plus z, and the other one that I need to do is, again, z minus z cross ay, so minus z points here, minus az cross ay will give you a plus x vector. Okay, so this in effect becomes, let's start here, hr is equal to, just going to bring this one, write it on top of here, this coefficient, let's make a nice coefficient, er0 over eta 1 sine theta r az plus cos theta r ax e to the minus j beta 1 x sine theta r minus z cos theta r. Okay, that's an angle theta. Okay, so I have this expression now for my incident field and my reflected field. The last one that we've got to do is we need to figure out an expression for them. Okay, so, well, firstly, sorry, before we get to this, let's check. So I said I wanted a plus x component for my reflected magnetic field and a plus z component, and this is what I got, so all good. Okay, let's find now an expression for my transmitted field. Okay, so transmitted field works exactly the same. HD. The only difference is now I work with eta 2, the intrinsic impedance of, sorry, my makeshift camera system is vibrating. It's a wire, blow dart as we call it, right? That I built with a webcam. Okay, so in any case, we need eta 2, which is, because we're using eta 2 because we're working with a magnetic field. We want to find an equation for the magnetic field here in region 2. And over here, I have intrinsic impedance eta 2. Okay, that's just simple. That's why it is like that. Okay, so now the general equation is ANT cross ET. I have that and I have that. And we substitute them in. They look like this. Sine theta t in the x direction plus cos theta t in the z direction cross, so this over here, just recap, that's ANT that we calculated in step 1, cross a y e t0 e to the minus j beta 2, remember, because I'm working in region 2, and this is just x sine theta t, sorry about the space here, they got a bit cramped, plus z cos theta t. Okay, so again I can perform ax cross ay, which, if I look at my little axis, ax cross ay will give you plus z, and I can perform a z cross ay, a z cross ay, from z to y, thumb points in minus x, so it's minus ax. Okay, so this in effect will give you something that looks like this. Transmitted magnetic field is E T0 over eta 2 sine theta t in the z direction minus cos theta t in the x direction e to the minus j beta 2 x sine theta t plus z cos theta t. Okay. What do I have now? I have now expressions for my incident magnetic field, reflected magnetic field, and my transmitted magnetic field, with as expressed as functions of theta t and x and z. Okay, now, and I also have expressions now for EI, ET, and ER. Okay, let's figure out what's going to be next. Okay guys, sorry. So what we're going to do now is we have found expressions for, essentially for EI. We have EI, the incident electric field, the reflected electric field, and the transmitted electric field, right? In the context of this this case where we have over here, we have some interface here on the that's aligned with the x-axis here, region 1 and region 2, and we have some, obviously in region 1 there's some material with relative permittivity epsilon r1, mu 0, non-magnetic material, and in this region epsilon r2 and also mu 0, so non-magnetic material. Okay, and we've found now expressions for EI, ET and ER, and also for the magnetic fields. So we also have then HI, HR, and we have HT. Okay, and this was found to be consistent also with the direction in which these waves are orientated and in which they are propagating. Okay, so now what do we have to do? We have seen that these are functions. We have some unknown coefficients for the reflected field and transmitted field, and the same ones for the magnetic fields over here. So I need to figure out how can I solve those. Okay, because these are the only real fields we know. So in order to solve those, so we can solve for, remember, ET0 and ER0. These are the coefficients, and likewise theta t and theta r, and we do this using what we call boundary conditions. So that's just a shorthand for boundary conditions. So boundary conditions, there are essentially two that we can use in this case. The first of which is related to the tangential electric field. Okay, so let's do that. So we are going to do this now. Step 4 is relate theta I, theta r, theta t, and EI0, ER0, and ET0. And we're going to do this using the tangential component of the electric field. So let's do that. Okay. So the tangential, if you look at the formula sheet, essentially you have something that looks like this. You have AN cross E1 minus E2 is equal to 0. This tells me that the tangential field across some boundary, some interface, remember that's the interface, this is region 1, this is region 2, and my normal points from region 2 to region 1, and this is AN. Please do not confuse this vector, which is just the normal vector between medium 1 and medium 2, with these little vectors over here. That is, these vectors are associated with the TEM, the transverse electromagnetic wave, that shows the propagation direction of this field. ANI, ANT, ANR, and these one, that is just a normal vector pointing from region 1 to region 2. Nothing to do with those ones. Okay, so essentially we have this. Now we need to, but if we, okay, so let's find E1. E1 is the field, all the field, the total field in region 1, which is the sum of EI and ER. My vector AN that points from region 2 to region 1, in the context of my problem, if I have a vector point, if my interface is here, the point at which z is equal to 0. Let's make it a little bit more clear. Now, let's use some color here to denote that. So this is my interface, okay? My normal vector, there, this normal vector, an, is equal to minus az. Now, I'm pointing from region 2 to region 1 in the minus az, because z goes that way. So minus az. Okay, let's do that. So it's fairly simple. It's minus az, an, cross E1, which is now the total field in this region. That is EI plus ER. Let's do that. So it's EI plus ER minus ET is equal to 0, because this E2, remember here is E1 and here is E2, and if I look at my little drawing here, E2 is just equal to this part, the transmitted electric field. So here I have this. And then it's simple. Then you just substitute your already known expressions for EI, ER, and ET into this equation. And we can do that. So it's minus AZ cross essentially all of our electric fields. Let me just get my paper where I calculate that. I am going to show you that now. Remember, this was my paper where I calculated these ones. So all these fields, EI, ER, and ET, they are all just dependent on AY. Okay, and that's also consistent with my problem setup. Now, EI, we're looking at the perpendicular polarization case. So all our electric fields are just coming out of the page over here, all polarized in Y. So I have minus AZ cross AY times, and then I'm just going to substitute in my expressions for the electric fields in here. So I have EI0 e to the minus j beta 1 x sine theta I plus ER0 e to the minus j beta 1 x sine theta r minus ET0 e to the minus j beta 2. Remember, these little subscripts are important. X sine theta t is equal to 0. Sorry, space got a bit cramped over here. That's a t. That's theta t. Okay, so what is AZ cross AY? If I look at my little drawing, very quick, let's just make it like this. These little Z hat, that's just a short way to write that. So I have minus AZ, so it's minus AZ cross AY will give you, if I go here, this cross this will point in the plus x direction. So I have AX and this term over here is equal to 0. So essentially, if I need to solve this, well, then this coefficient has to be equal to 0. Okay, so I have the case where okay, before I write it down, I can also see that, remember, Snell's law says that this angle, I have a field going in here from physics, that is Snell's law. I know that this angle has to be equal to that angle. So, and I have Snell's law telling me that theta I is equal to theta r. Then this expression set equal to 0 can be simplified a bit. We can write this is equal to EI0 plus ER0 e to the minus j beta 1 x sine theta I is equal to I just take that to the other side of the equal sign here. It's equal to ET0 e to the minus j beta 2 x sine theta, that's an angle theta t. Now I am getting really close. So this is just a complex number in polar form, some coefficient, some angle, some coefficient, some angle. For these two complex numbers to be equal, I have EI0 plus ER0 is equal to ET0, and I have the case where this and that argument has to be equal. So beta 1 x sine theta I is equal to beta 2 x sine theta t. Awesome. So that is a fairly important result. That's one equation. Remember, eventually I want to solve ER0 and ET0 in terms of EI0. So I have one equation in which I can do that. But I also now have an equation for the angles, relating the angles. And this, I can rewrite a little bit to look like this. I just divide by sine theta. So it's sine theta over sine I. Sine theta I, the incident angle, is equal to beta 1 over beta 2. And this is also known as Snell's law of refraction. These are two fairly important results. If I ask you to derive for me a relation between the angles and the coefficients, then this would be the way in which you do it. Okay, something that I just want to point out here that might be a bit tricky is if you look at the expression for EI, ER, and ET, just put it back here, then you'll see that the waves, the fields that I substituted in here, specifically the coefficient, the angles, there's also another term actually in each of them. What is that term? Let's just open this. What is that term? So that term is, if we look at this part over here, that's EI0 e to the minus j beta 1 x sine theta I. But the full one is actually EI0 e to minus j beta 1 x sine theta I plus z cos theta I. And why does that fall away? Because I am applying my boundary condition at z equals 0. So this, if I just put a 0 in, e to the power 0 is just 1. Okay, that's why I only retain this first part. I hope that's clear. If not, you're welcome to leave a comment and then we can look at it. Okay, so now I have essentially one equation, and obviously another one that's important is this, which is Snell's law of reflection. So reflection, Snell's law of refraction gives us this, and I have one equation for my unknowns. Okay, I need another one if I want to sort that out. So let's see if I can use another boundary condition to do that. Okay, so we've found one equation using the tangential electric field. Let's see if I can use the tangential magnetic field boundary condition at the interface. So at z equals 0, we have, if you look at your formula sheet, an cross h1 minus h2 is equal to, remember, it's some surface current. But what do I have now here? I have dielectrics, right? I have a dielectric here in this region, and I have a dielectric here in this region. And we have, it's non-conductive material. So sigma is equal to 0. So another condition is, or another case here is I know that sigma is equal to 0. So this surface current does not exist, okay? So at z equals to 0, I have this case. Now, again, my normal vector points from region 1 to region, from region 2 to region 1, and in this context, it's equal to minus az. Okay, so I have a minus az, and I'm going to cross it. So again, H1 is the total magnetic field in region 1. It's equal to HI plus HR, and I'm only interested in the components where Z is equal to 0. So if I do that, I can simplify my expression to look like this. It's EI0 over eta 1. Let's move that out of the picture. I'll bring it back if needed. EI0 eta 1 minus cos theta I in the x direction to the power E minus J beta 1 x sine theta I plus ER0 over eta 1 cos theta R AX e to the minus J beta 1 x sine theta R, gonna go on here, minus ET0 over eta 2 minus cos theta T AX e to the minus J beta 2 x sine theta T, right, is equal to 0. So, this was just the substitution for H1, which is HT plus HR, and H2 is H2 is HT, and H1 is HI plus HR. Okay? Look at here. So H1 is that magnetic field plus that magnetic field, and in H2 I have that magnetic field over here. Okay? That's what I have. Then I can simplify this a bit. So what we can do is, obviously, if I have some vector, some coefficient is equal to 0, it means that this coefficient has to be equal to 0. Let's write that down. And maybe let's also see if we can get rid of these fractions. So I'm going to multiply each term by eta 1 times eta 2, multiply this by eta 1 times eta 2, multiply by eta 1 times eta 2. Then I'm going to get rid of those fractions. Okay, so then I have something, and I'm only going to work with the coefficient over there that should be 0 for this vector to be 0. Then I have something that looks like this. I have a EI0 eta 2. Remember, I multiply eta 1 times eta 2 with this, then just EI eta 2 remains because eta 1 over eta 1 is equal to 1 times cos theta I e to the minus J beta 1 x sine theta I minus ER0 eta 2 cos theta R e to the minus J beta 1 x sine theta R, and this is equal to ET0 eta 1 cos theta T e to the minus J beta 2 x sine theta T. Sorry, it's a bit pressed in here. That's minus J beta 2 x sine theta T. I will upload all these calculations also. Scan it and upload it so you can follow it there. I've just written on the left-hand side these two terms, and I've just taken this term over to the right-hand side over here. But that should be okay, right? EI0 eta 2 cos theta I, this one, minus ER0 eta 2 cos theta R. But what do I know? I already know, we already know that theta I is equal to theta R, right? That's Snell's law of reflection. And I also know that beta 1x sine theta I is equal to beta 2 x sine theta t. Oh, now I can factor out those two exponentials. So I can write it like this. EI0 eta 2 cos theta I minus ER0 eta 2 cos theta R e to the minus j beta 1 x sine theta R is equal to, I'm going to write the second part over here, is equal to E T0 eta 1 cos theta t e to the minus j beta 2x sine theta t. Okay, so that is in effect equal to that, because I have beta 1 x sine theta I is equal to beta 2 x sine theta 2, exactly what's here. So that means this part and this part has to be the same. So I have another equation. I have this. EI0 eta 2 cos theta I minus ER0 eta 2 cos theta R is equal to ET0 eta 1 cos theta t. So now I have two equations that I can use to relate EI in terms of, or ER in terms of EI, or ET in terms of EI. So that's the next step that we're going to do. Okay. So essentially, what do we have? Now we have two equations. We have EI plus ER0 is equal to ET0. This came from the tangential electric field continuity at the interface where Z is equal to 0. And I've just now, using the continuity of the magnetic fields, calculated this. Now, I have calculated this now. Okay, and yeah, so from the continuity of the magnetic fields, I have this ER0 eta 2 cos theta R is equal to ET0 eta 1 cos theta t. So one equation, second equation. So let's see what we can do. This one we can rewrite a little bit differently. I can also obviously substitute this for ET0 in, yeah. Okay, so then I have something that looks like this. I have EI0 eta 2 cos theta I minus ER0 eta 2 cos theta R is equal to EI0 plus ER0 eta 1 cos theta t. And then I can just simply group all my EI0 terms, and I can group all my ER0 terms. So let's, on the left hand side, group EI0s. So EI0, and this is just eta 2 cos theta I minus this part eta 1 cos theta t, and this is equal to ER0 eta 1 cos theta t plus, just take that part over, plus eta 2 cos theta r. Now I'm getting very close. So I can now write that if I have something, a coefficient times EI0 and a coefficient times ER0, I can now find an expression for ER0 in terms of EI. So I have this. Eta 2 cos theta I minus eta 1 cos theta t divided by eta 1 cos theta t plus eta 2 cos theta r times ei0. I can also write this a little bit differently by just bringing out some of these. This is this additional step. It's not critical, but it allows you to relate this to something that we saw also for when we worked with conductors. Right. So I just factor out, in my numerator I factor out cos theta t times cos theta I, and then it becomes this. Eta 1 over, this is a minus sign, eta 1 over cos theta I divided by eta 2 over cos theta t plus eta 1 over cos theta I. Right. ei0. And obviously that and that cancels out. So another way to write this is also in terms of this coefficient over here, where this coefficient that we call the reflection coefficient. Okay, so I have the reflection coefficient, and I write this because remember we are looking at the perpendicular parallelization case over here, né? Perpendicular, so E is perpendicular to the plane of reflection. So now I have this given by, if I look over here, it's given by eta 2 cos eta 2 over cos theta t minus eta 1 over cos theta I divided by eta 2 over cos theta t plus eta 1 over cos theta I. And you will see that if you let the angles equals 0, right, then this just reduces to the normal incident case, which we also reviewed in class. And following a similar manner, I can also calculate an expression for the transmission coefficient, which is given by tau, and that is just now I'm going to relate, tau comes in when I relate the transmitted electric field in terms of the incident electric field, right? And this is just a normal component. But the same, exactly the same approach applies to the parallel polarization. So you can follow the exact same steps to calculate the reflection coefficient, for example, for the parallel polarization case. So that would be where EI is now lying in the plane of incidence in the XZ plane, but you follow exactly the same steps. Okay, so that's it for this part. I hope it was clear. If not, please send me questions.